Chuck Mitchell. I'm on the board of the Seventh-day Adventist Forum in San Diego here, as well as on the Adventist Today board, which I've known Irv for maybe close to 20 years now. And I didn't know a lot what he did. I knew he worked at UC Riverside there and was very knowledgeable about radiocarbon dating and anthropology and things like that. In fact, I was the person that recommended that we bring Irv down here. So we'll let him give his presentation. Thank you.
Thank you. Oh, thank you so much. I have discovered that there's a difference between the 805 and 605 interstate. I just discovered that today, but there we are. Looking over the list of your previous presenters, I was recalled that I've spoken for the forum, let's see, this is the fourth time. And last time was in 2010. But today I'd like to talk about a topic that often comes up in the popular media. It's the age, how old things are, various parts of the world we live in. And I wanted to focus today on how scientific research over the last century, actually, determined the ages assigned first to the earth and secondly to living organisms, and then to how it is approached, how long our species, Homo sapiens, we are the intelligent. We're supposed to be the sapien species, which I'll show a slide here suggests we're not sometimes. Now, it's clearly, from a scientific point of view, or an anthropological point of view, or an archaeological point of view, there's no problem, and everybody knows what the Earth is. But you'll find out, if you're not aware, having done some reading, that there's a definitional problem with human, what that actually means. And we'll get to that. Oh, by the way, I'm working off 2 PowerPoint platforms, and I hope this is going to work. It's my fault, not their fault. Okay, all I have to figure out is let's see. Normally I do this, and it works. So we're going to talk about 2 major issues. The scientific consensus, with just a second we'll talk about what that means, what it means for a scientific consensus, considering the age of life on our planet. And to do that, we need to talk about some geology. We need to talk about some paleontology. I think most of us know what geology is. Paleontology is the fossils, study of the fossils. And then the key thing, and the thing which has revolutionized this topic in the last 60, 70 years, is what we call geochronology. Explain what those are. Our second issue is the same consensus, scientific consensus, and how long humans have been on our planet. All right. For that, we do need all 3 of those scientific fields, plus what's called paleoanthropology, which you may have not run into as a term, but that's talking about the fossils associated with our species. Because some of the humans are fossilized, and we'll explain that in just a second. We're going to discuss this in the context of scientific consensus, and there's 2 parts to this. It's what scientific research has uncovered as data, information, and what kind of interpretations of that data is generally held to be valid within the scientific community today, what's sometimes called normative science. That is science that's practiced at the universities and gets grants from the National Science Foundation, the Institutes of Health, and that kind of thing. What do we mean when we talk about normative science or science? What we mean is that this first one is often not mentioned, but there is a consensus about worldview. Science has a worldview. And then there's the one we mostly know about is methodology. That's what we think of when we talk about science. But a worldview of science is very important. You don't have to accept the worldview. That's all right. But it is the worldview of the contemporary scientific community. And it's summarized in a term called methodological naturalism. Sorry. Methodological means the way we approach the world is assuming that it's naturalistic entirely. That is, the only reality is a physical or a naturalistic or a materialistic reality. Science does not deal with things that are not materialistic. It doesn't say it's true or false, or it just that's what science does ever since Newton, more or less. Then the methodologies, you're more familiar with those. Those are empiricism, that is direct observation, experiment, etc. To explain natural phenomenon. Science does not deal with anything else except natural phenomenon. That is, it doesn't deal with what we call supernatural. I mean, they don't have an opinion on it. They just don't deal with it. It is public evidence-based. There's no such thing as private scientific information. It's cumulative, and it's always tentative. And graduate students and postdocs just love to prove their professor wrong. And the professor wants them to prove that they're wrong. Now, we have egos, don't we? Oh, I'm sorry, you didn't know that professors have egos, right? I'm terribly sorry. We are a bunch of prima donnas in a lot of ways. And there's a thing called modeling and multiple hypothesis testing. Hypothesis is just an if-then question. If something is true, if we do an experiment, it should come this way. If it doesn't, our hypothesis needs to be changed. We deal with high degrees of probability, overwhelming weight of evidence. You very rarely see proof and truth as words in scientific narratives. And quantification, as you probably know, mathematics is often the language of science, particularly the hard sciences. All right, so that's the framework, the scientific framework. Now, how old is it? Well, first we're going to talk about the geology, which is how the Earth formed and some of its development. We're going to talk about paleontology, how extinct life forms, extinct, no longer living life forms, what were they like? And then what do we mean by fossil? Well, everybody knows about a fossil, but what it really means, or generally is used, is it's something that was once a biological structure, like a bone or a tree, which has been petrified, which has been turned into a rock replica. That's why it's still around millions of years later, because it's been turned into rock. There are what are called subfossils. This is where some of the material has been petrified. The other, you retain parts of the biological material. Then geological time. Chronology is key in geology, as it is in many of the sciences that deal with process. And then, how old has humans been on Earth? All three of those are important. You have to know those. But then, this thing called paleoanthropology. And paleoanthropology deals with what we call the hominin if you read books 20 years ago, it was hominid. Now, we like to change words just to confuse people. That's why we change words because the definition changes for reasons we have more data. So anyway, we study, paleoanthropology studies hominin primate fossils. That means hominins which are no longer living. They become extinct. Okay? Primates, what's a primate? We are all primates. By the way, you know why we're primates is because we do the naming. Humans do the naming. We're the first of the mammals. We get to name things. So we're the group of mammals characterized by larger brains, that is, brain cases, compared with body size. Obviously, a whale is going to have a bigger brain, okay, but it has a large body to deal with. Visual acuity, stereoscopic color vision, that's a characteristic of the primates. And opposable digits. It's very important. You know how much of the brain is just to do that? It's quite remarkable, I'm been told. Okay, this word hominin, that's the word that's used for the fossils. We don't use the word human there, because that's a kind of, has overlays of meaning. But from a scientific point of view, that is the group of primates to which we belong, but who does the naming? We do. We do the naming. So we say that this is the group of primates to which humans belong, along with other forms which are considered most directly related to us. See, we use humans for that. On the basis of what? Well, the new data, well, it's not new anymore, 30 years, is molecular genetics, or DNA, on living populations, and anatomical features for extinct populations. We'll get into that a little bit. So, a hominin includes the chimpanzees based on physical type, the organization of the body, and a very similar set of genes. How similar we are to the chimps is a matter of discussion, but it's in the 98, 99, 97% So it's not that we're not special because of genetics. We have other more important things. We call that culture, cultural learned behavior. That's what makes us unique. Chimp can walk bipedally. They don't do it. They're not habitually bipedal, but they can. But what is distinctive is for our genus, which is Homo, H-O-M-O, Homo, our characteristics that set us apart are culture-based, learn-based, and that takes a big brain and a very complicated set of symbols, which we call language, which is very important in that. Okay, let's start with the Earth, because we're going to talk about how long you have to deal with this material on which living organisms are formatted. To do that, I liked, when I was lecturing freshmen particularly, always emphasize you're nothing. You are a small organism on a small planet in a small solar system on the edge of a huge galaxy. Now, you'll never be able to see that galaxy. This is a reconstruction of what our galaxy looks like. We're the second arm in, but the whole galaxy is about 100,000 light years across. But there are billions of these in the known universe. So I've always emphasized that this tells us something about our scale of our abilities here. This is our sun, I don't think you can even see it, from the edge of the arm of our galaxy. Okay? But, okay, let's get now. Here we are in San Diego on planet Earth. This is based on satellite imaging. All right? But we live on the crust. We live on the crust of the Earth, and that's the outside shell is about 1% of the Earth's volume. The thickest part of the crust varies on the continents, varies between 20 and 30 miles. I should have put the metric. Scientists don't use miles. They use kilometers or meters, whatnot. Anyway, we're on the crest of the Earth, and we float. The crust floats on the underlying mantle rocks. And here is the current situation of the plates, the different plates moving in different directions. We all know about the San Andreas Fault. That's the biggie. That's on the edge of the current Pacific and North American plate. All right? And that's the one that's moving and will be around San Francisco in about 13 million years. So just wait around. You don't have to travel to San Francisco. The other thing that's interesting is what's called the Mid-Atlantic Ridge. Okay? That's halfway between what is now South America and Africa plate. But many years ago, many years ago, they were all together in a thing called, let's see if this works. This is the one I had. It works. It's called Pangea. All right? And an interesting thing about Pangea, this is when the southern continental masses were closer together. And over geological history, they've moved back and forth. Okay? One of the things that indicated to them that this was what was happening is a distribution of a number of fossil species could only be explained by assuming that at some time these continents were close together. And one example is a fern which shows up in South America, Africa, India, Antarctica, of all things, and Australia. That kind of tells you that, and it's all the same species fern, apparently. It's quite interesting. But let's look at the stratigraphy of geological structures. By stratigraphy, we mean how it has been built up, layer by layer, over time. And to give it a scale, can you see them? Just barely. There's supposed to be a human there. Okay, it's about 6 feet. Anyway, it gives you a scale. Can't see. And of course, time goes that direction, bottom to top. Normally, most of the time. So one of the foundational elements of geology is a study of stratigraphy. Strati means layer. So the layers of the earth. Now that gives you a better scale on the right. But sometimes they're not horizontal. There's very convoluted sedimentation and stratigraphy. Sometimes very good. If you want to see some really good stratigraphy that is very complicated, it's north of San Bernardino. As you go north out of San Bernardino, there's a bunch of badlands, and that's where the San Andreas Fault comes through, and it's a very, very complicated stratigraphy. The question is, how much time is involved in the accumulation of all this, of these rocks? These particular rocks are the rocks. The place where a lot of this has been studied for almost a century is in the Grand Canyon. I assume a lot of people have been who's been to the Grand Canyon? You've all seen one of the great geological wonders of the world. cutting through the Colorado River, cut through a huge amount of the sediments. Now, the only reason we see these sediments here is because it's been cut away. In other places, these stratigraphy is there, but it's all covered up. This is Zion Canyon, same thing. And then this is Bryce Canyon. Now, these are all within they're close to each other, within 100 miles of each other. And what's remarkable is, as you go through the stratigraphy, beginning with the Grand Canyon, you can compare the Grand Canyon with those other two exposures. And at the Grand Canyon, you have three sets of rocks, what they call basement rocks, early rocks, and later rocks. Very informative, right? Three big groups of rocks. And time obviously goes in that direction, from bottom to top. When you talk about stratigraphic analysis, there's no magic about it. It's pretty commonplace. Things below other things are usually older than things above, which are younger than things below. That's a quote from a textbook, very expensive textbook. Okay, well, if he can get away with writing like that, I can too. With the emphasis on the word usually, there are what's called overthrusts, which sometimes confuse things. But anyway, generally speaking, that's true. How much time was involved in laying down all of the stratigraphy, all the sediments, all the rocks? We're interested in that because they also contain fossils in the rocks. All right? So it's not just the rocks, it's the former life forms that are preserved. And over the last 150, 175 years, geologists have gone all over the world studying the various stratigraphies and has come up with names, generic names, for these layers. One is Precambrian. In the Grand Canyon, there is no Cambrian. We'll get to that. The rocks in the Grand Canyon are Precambrian, Ordovician. These are all names from the Old World, primarily, applied here. Devonian, Mississippian, Pennsylvanian. That's where the coal, when you dig for coal, that's what you're looking for. You're looking for the Mississippian and Pennsylvania strata. And then Permian. Now that's the sequence. That's at the Grand Canyon. There's a bunch of rocks that are missing from that area. The Cambrian is missing, the Silurian, and some of the Devonian is missing, and the Triassic, Jurassic, Cretaceous, Tertiary, and Quaternary are all missing. How do they know that they're missing? They're not there, but how do you know that they exist? Well, the reason is that there are a lot of comparisons on rock type and the kind of fossils they occur, but most important is isotopic dating methods have indicated what are the ages of these rocks, and other places the same ages, which do contain fossils. Okay? Looks like I've jammed this up against the left. Okay. Why are they missing? The reason they're missing is because of erosion. And the erosional surfaces are called nonconformities by geologists. Now, some nonconformities is very hard to tell unless you're a card-carrying geologist. You have to get in there and you have to know what you're doing, you look for evidence. Sometimes it's very hard. Most of the time it's not. Most of the time it's not, I'm told. Here are the big eras of geological time. Many of you have probably seen these terms. There's the Paleozoic, Mesozoic, Cenozoic. All it means is old, middle, and recent life. Zoic is life forms. Okay, early Meso and Cenozoic. The periods are the ones that we were using from the Grand Canyon, and then they're divided into, some of them divided into early, middle, and late. This is the Mesozoic. This is where the dinosaurs were. And then closer to our time, our, quote, our human, hominin, sorry. I'm old. I still have to fight the difference between hominid and hominin. Sorry about that. My students say it's just because you're old and losing it. That's what they say. Anyway, time is going from the bottom to the top. All right, and the question might be is where are we in this geologic? We're at the top. We're at what's called the Holocene and the Pleistocene. Pleistocene is the Ice Age, during where great continental ice sheets existed. Okay. Now let's compare Grand Canyon sequence, which goes from, there's Precambrian, and I'll explain Precambrian in a second, to Permian. And if you add the Zion National Park sequence, it goes from Permian to Jurassic. And then if you add the Bryce Canyon, you go from Jurassic to Tertiary. So those three exposures within 100 miles of each other give you almost all of the geologic column. It's very fortunate. In those rocks are, of course, here and other places dated as the same level by the dating methods, which I'll talk about later. It is one of the gold mines of geology, because you have so much of the geologic column that is exposed. So that when you combine these, you have a listing of most of the major groups of living organisms. The Grand Canyon goes from the invertebrates in the Precambrian up to the small, very small reptiles. And then the Zion Park includes periods of the dinosaurs and the earliest mammals, very small mammals. And then, and it also includes the birds. And then in Bryce Canyon, you have the rocks that contain the flowering plants and the mammalian divergence. And finally, you come to our group, which is way at the top, the primates. So we have then the Grand Canyon with the Paleozoic, the Zion with most of the Mesozoic, and Bryce Canyon with much of the Cenozoic. Now, there are no primates in the Grand Canyon. All the primate fossils are in Africa. All right. The fossil forms, and as modern primates are primarily African. Not always. So some are in South America. Okay, how many of you have heard of the Big Hit, which is where a large asteroid hit the Earth somewhere in the Yucatan Peninsula, which is now called the Yucatan Peninsula, and did a lot of damage, caused a lot of destruction. And one of the things happens was, this is apparently when the dinosaurs were killed off, maybe directly or indirectly. All right. The other thing that's observed when you go through the fossils is, as you come up the geologic column, there is an increasing complexity in the organisms. Now, just life itself is complex, so this is a relative term. All right? And historically, how did this idea of the increasing complexity of organisms, how did this get started as an idea in geology? Well, interesting, it comes about from very practical economic reasons back in the 19th century, middle of the 19th century, in England particularly. There was the reason it was studied was for practical economics. where they wanted to not have to go around the landscape kind of randomly looking for the right rocks that have coal or iron ore. They wanted to be able to be efficient. So they hired what was an ex-surveyor, a guy by the name of Bill Smith, and he was, as I said, a surveyor primarily, didn't have any university education, but he went out and looked at the sequences. The sequences were being produced when they were building railroads in the 19th century in England and cutting through, and he was able to see the stratigraphy. They also cut through for canals, and he saw the stratigraphy created when they did that. And he came up with the idea of index fossils. Index fossils. He determined as he went around the geology and paleontology of England that it was not just a random operation. Things went together. This kind of fossil was always found in this relationship to a particular rock forms in England. All right? And so he conceived of, if you dig a place and look for a particular fossil, and secondarily, looking for particular kinds of rocks, you'll have a tendency to find what you're looking for. If you know already that below this fossil is coal, so you go and you find the fossil, then you expend hundreds of thousands of pounds to excavate the coal, but you don't do it just on a random basis. So the fossils became diagnostic of specific stratigraphic levels. And the idea was expanded because it worked into all the world. And geologists all over the world used that idea. Okay, now, if we come forward in time to all the benefit of all this data, what do we know, what do geologists know about the sequence of events associated with the formation of the Earth? Well, you have a beginning in time, and you do see very simple organisms in early rocks, okay? And what has been discovered is, at some point along there, photosynthesis begins. That is, there's enough biological change that organisms were able to use sun energy. And this is a very complicated thing. This is not simple. That produced oxygen. There hadn't been a lot of oxygen in the atmosphere. And that produced oxygen. And then you, 3/4 of the way around, you get the earliest hard shell fossils. And then you come to the Paleozoic, Mesozoic, Cenozoic. In other words, about 85% of the geologic record on the Earth predates the beginning of those more complex organisms. And that period, so you had the Cenozoic, finally with the Cenozoic at the top. That whole period is called the Precambrian. And that's, what did I say? It's more closer to 90% of the geological record is in the Precambrian. And those rocks contain fossils. And here is a simplified summary of the groups of organisms that appeared in the geologic column and their relative abundance during different geological periods. One of the things they've discovered is what is called the Cambrian explosion. Turns out that in the interface between the Precambrian and the Cambrian, you had a huge proliferation of different types of fossils, what we call fossils today, living organisms. Huge proliferation, very relatively quickly in geologic terms. But again, how much time is involved in this, and how do we know? it's only in the upper parts of the geological column that we would have fossils that look like organisms that we see today. If you go farther down in the geologic column and fossils, they don't look like anything we have today. They are totally extinct, and different life forms had existed. Now we come to as it were, the secret of how they can talk about time. And this is an important point. It needs to be emphasized, I think. Geochronology is the study of geologic time. And what are geologic ages? When a scientist says, oh, this particular sequence is 10 million years old, how do they know? You can't tell from the rock itself. It doesn't have a little sign, I'm 10 million years old. We do it by a series of isotopic dating methods, which are fascinating history. My own professional life is just one little piece of that, radiocarbon dating, which only works for very recent, last 60,000 years or so, and only on living material. But we're talking about rocks. How on the devil do you date a rock all of a sudden? Well, first of all, let's define words. What do we mean by isotope? Remember your high school chemistry or college chemistry if you studied geology? What's an isotope? An isotope, first of all, you go and say, what's an atom? Well, atoms, we all know about atoms, the basic physical unit. And I'm just told there are now 118 different types of atoms. Okay, they just named one. And I can't pronounce the name, it's a Russian name. But all atoms exist in terms of one or more types, and those types are called isotopes. Okay? Most atoms have multiple isotopes. A few just have one isotope. And some, well, I'll get to that. Okay. So there are, these types are called isotopes, and they only have two forms. They're either stable, that is, they just sit there and don't do anything except sit there. And then there's the unstable isotopes. That's what we call radioactive isotopes. They change. Unstable isotopes are called radioactive isotopes. Okay? Let's take carbon, for example, which what is a third of us? 30% is carbon in us, in any living thing, I'm told. So we take carbon. It has 3 naturally occurring isotopes. And now that we use numbers to refer to them, and I won't go into the physics of why they do that. But anyway, there's carbon-12, which is stable, and that's most, 99 plus percent of all the carbon on Earth. There's carbon-13. It's also stable. Just sits there, doesn't do anything. That's 1%. And then we have the star of the dating methods, carbon-14, which is radioactive, but there's not a lot of it, 10 to the minus 12. So, but we've got one carbon type which is radioactive. When we talk about radioactivity, kind of 4 things we might want to mention. Every radioactive isotope will periodically decay or disintegrate. Or I have a friend at Berkeley that says it explodes. Okay, that's radioactive isotopes explode every once in a while. So you throw off some sort of nuclear particle or sometimes nuclear radiation, like gamma radiation or X-rays. And it turns into an isotope of another element which is stable, or it can turn into something that's also radioactive. Okay? The rate, and this is the key thing for radioactivity, the rate at which populations of the same radioactive isotopes decay with few exceptions, there are few minor exceptions, is fixed. It doesn't ever change. Good reasons for that, our physics colleagues tell us. And it's a unique value. Only that isotope, that radioactive, has that value. And this is a much studied phenomenon. It's confirmed every time somebody tested it, and they don't do it anymore because it's kind of rough. You don't put graduate students on something they know happens 99.99999% of the time. There is a form of decay, which is called electron capture, where the rate can change by a few percent because of certain chemical changes. But that's the only exception. And we don't have any dating methods based on things which have electron capture. Well, that's not true, but it's not important. If you have certain conditions, these fixed value can provide equal ticks, as it were, on a nuclear clock. It's very, very accurate in terms of incrementing time. And that fixed value is called the half-life of a particular radioactive substance, half-life. Half-life is a simple idea. It just means the length of time it takes for a radioactive isotope to decrease by half, or 50%. All right? So it goes from 100% to 50%, and that's one half-life. Straightforward, very straightforward. Half-lives can range from a few minutes in naturally occurring to billions of years. And the technique that's most often used for rocks has a half-life, potassium-40 has a half-life in the billions of years. Let's emphasize something. That's because it's kind of important for a purpose. When you talk about geological ages, any kind of geological ages, they are almost entirely determined on the basis of the application of what? Question time. Isotopic dating methods. That's what's behind almost all the ages. And each dating method depends on decay rates, which are fixed and used as clocks. And we know by very, very long physical observation, more than a century, 150 years now, that these are fixed. Most of them, 99% of them are fixed. But the problem with isotopic dating methods is they require some rather specific conditions under which you can use them, and each one is different. Well, here we have a radioactive isotope. What does it do? It throws off different particles, alpha particles, negative beta particles, positive beta particles, and radiation, in this case gamma. Okay? So we take carbon. Here we take carbon again. Here's carbon 12, 13, and 14. Two of them are stable, and C14 is radioactive. Okay? So if it's being radioactive, it will decay by throwing off a beta particle, negative beta, and turning into, it throws off an antineutrino. That's something only a physicist can appreciate. That's not for us important. It turns into nitrogen-14, which is a stable isotope of nitrogen. Okay? And that's the basis of radiocarbon dating, that phenomenon. The half-life of radiocarbon, we wish it would be much longer, but unfortunately it's not, is about 5,700 years, roughly. And now we know what that means is if you have 100% of radiocarbon and then go away and play golf or tennis or something for 5,700 years, how much will you have? 50% of it will be there. And that's one half-life, okay? But if you wait around another 5,700 years, or 25, half of 50% of 50, you've got two half-lives, 11,400. All right. These are slow, I'm sorry. So there's 25%, and that's about 11,000. And then that's two half-lives. So if you go out, say, 9 or 10 half-lives, you go out about 9.6, you go out to 55,000. So that's close to the 60,000. That's the routine end of radiocarbon dating. It's about 60,000 years. It can only work on once living materials such as wood, charcoal, shell, bone, that kind of stuff. But what about rocks? What about rocks? Okay? Well, when we go to rocks, you can use other isotopes with much longer half-lives, and particularly in environments where you had volcanoes. All right? And this technique is called potassium-argon dating. There's a variant of it called argon-argon, but it's the same idea, just a different variant. There's another one, rubidium-strontium. The third, samarium-neodymium. Fourth one, uranium-thorium. Okay, those top three are on rocks: uranium, thorium, iodine, xenon, lead, and uranium lead are also on rocks, but different kinds of situations, not volcanics. So, okay? Why is radiocarbon? Well, we already know. Why isn't it listed here? It doesn't date rocks. It only dates living things, once living things. And it can only go out to 60,000. Okay? How does potassium-argon work? Really quick. Potassium-40, here's those numbers again. Different radioactive isotopes have different numbers up there because that's how many protons and neutrons. That's just a physicist can love that kind of stuff. Decays into argon-40. With a half-life, now we're getting someplace, 1.2 billion years. That's B with a billion. Okay? And so the half-life, so if you wait around and let it decay for one half of it, you've waited around 1.2 billion years. And as the potassium-40 drops off, the argon-40 goes up. So the ratio between those is your indicator. Argon is a gas. It's very important for this technique. It's a gas. It is a non-reactive gas because of its outer orbital electrons. They're non-reactive, so it doesn't react chemically. And when volcanics, this is what it's usually applied to, are molten, the accumulated argon-40, which had been in there for a long time, is outgassed, goes away. Okay? That zeros the rock as far as argon-40 is concerned. Now, here's a situation of where you've got a volcano throwing out lava, but also throwing out volcanic ash, or tuff. All right, deposited it on the landscape. The argon escapes, and the tuff winds up as part of a sediment. All right, so when it cools, you've got an ash layer which can be dated by potassium-argon. All right, when it cools and solidifies, the argon-40 begins to accumulate again. And the amount which accumulates from that point is a function of how long since that lava or ash tuff cooled. Now, we always put this last one in. There are a lot of variables. People who do this, there's a lot of ifs, ands, buts, and technical details. Okay, so here's what happens after you've run thousands of individual potassium argon dates and other isotopic dating methods. What do you say about the ages of this particular sequence of events on planet Earth? Well, according to that data, the formation of the Earth is about a little over 4.3 billion years, roughly. The earliest life, very simple life forms, are about 4 billion. Photosynthesis begins about 3 billion. Oxygen rich by 1 billion. Earliest hard shell fossils, this is the beginning of a fossil record in a great deal, is 500, and you get the remainder of the fossil record at Paleozoic is 250 to 65 million, and the Cenozoic is 65 to now. I'm going to kind of rush through here to finish, but here's the dates that you get on the various levels. Can you tell me when it's 5 minutes? Yes. Thank you. So tall, all right. Where are we? Where are Homo sapiens? Well, let's hold that question just for a second. So we have long ages for life, 4 billion as much. Organisms, 4 billion. First 3.5 living forms. The hard shell is about 500 million. And plants and animals, which we're familiar with as Miocene and Pliocene, that's about 20, 50 million years ago. And the group of mammals, which look similar to us, the primates, come about 10 to 15 million years ago. Now it's moved to ours, and we'll work through this. Remember, we're not called humans, we're called hominins. And the definition, it's biological taxonomy, that's the names we give to things. And historically, that taxonomy has been a contest between what we call lumpers and splitters. So that's why you'll see changes in the terminology over time. All right. Here's, for example, here's a very intelligent member of our species about to cut off a limb. But, you know, we're intelligent. Right? We have chimps, gorillas, orangutans, and old world monkeys. All right? And these are called the anthropoid primates. Anthropoid means looks like us, more or less. These are the old world monkeys, baboons, and another old world monkey. They have names for the whole group. Is in a superfamily. If you eliminate the monkeys, you have another group called on the family level, another subfamily level, and then you come to us, which today includes the humans and chimps, and they are the hominins. Okay? They are most directly related, but not us, not Homo, because that's a cultural definition. So biologically, we're a relatively hairless, this is for Homo, this is our definition, we're relatively hairless primate mammal, habitually bipedal, frontal lobe brain, we have a large frontal lobe. And then, but what's important is culturally a learned behavior, tool using adapted, complex symbol creating and manipulating, and complex language. That's what we're unique among the primates. All right? So that's the list. And how about in fossils? What are you going to look for in fossils for that? Well, the relatively hairless, can you find hairless? And no. You can't do that in a fossil. Habitually bipedal? Yeah, it's in the pelvis. You can tell it by the pelvis. Frontal lobe brain? Yeah, if you've got the skull, the front part of the skull, you can tell. The other stuff, it's difficult, perhaps, but very difficult. That's the archaeological problem. All right? The time, and if you look at the fossils, we're going to go through this very quickly. You have a group, these are the fossils that have been dug up. All right? And you have a number. These are very, you've got what are called non-hominid. Don't worry about it. They have a brain size about the same as a chimpanzee. This is another one about the chimpanzee. Then there are 3 fossil groups of hominin. One's called Australopithecus, the other's called Paranthropus, and finally us, Homo. But there's a bunch of types of Homo. Here's Australopithecus, 380 to 430. Here's Africanus. That's the Australopines, and they're all extinct. You have the Paranthropus. One of them is Boise, about 500 cc's size brain. They're extinct. All of them are extinct. Then you come to us, Homo. You have quite a few. Here's Habilis, about 5 to 6. Egaster, 7 to 800 cc's. Homo erectus, 600 to 1100. He's in the range of humans. And then finally Neanderthals. You've all heard of Neanderthal. They are in the same range as we are, roughly. There are differences between the skulls, but we are the same genus. So here we are, but all except one is extinct. That's us. We're the only one that's living today, okay? And our brain size runs from about 1,000 to 1,500. You can tell us because we have a forehead. Okay, how old are these fossils? How can they be dated? Well, they're dated potassium argon, remember? They're in rocks that can be dated. And they're dated because you've got multiple volcanic eruptions, thank you, and which lays down layers in the same environment. And you can do the stratigraphy, and in this particular locality, you know that 17 and 23, the stratigraphic levels, are tuffs, were laid down, we know the ages of. And there's an excavation, remains of a hominin between those two. And below, you know, has to be older, and above has to be younger. So that's how you bracket the ages of a lot of these. So you've got potassium argon, that's the one that's used, but radiocarbon can date young Homo. You've got uranium series, electron spin resonance, these are all foreign names to you. But there are many, many dating methods, multiple, that can be used for this. And that's the range. These ones that for our kind of animal, the last 5 million years. So, what's the age here? What are the ages of these? They range from present to about 5 million years. And they are in sequence. They're in chronological sequence. And that's how they're associated with the geologic column. Now, here's the hypotheticals. If you are going to argue that they are descended from each other in various ways, see all the question marks? That is a difference, huge differences of opinion about that. They aren't in the fossils. You can't tell the relationships, genetic relationships in fossils. They don't preserve the DNA. What have we not talked about yet? Evolution, right? Biological evolution. Now, the reason I bring it up is the data to deal with evolution and the idea of deep time are two entirely different sets of data and interpretations. You have the idea of deep time, and then you have the idea of process, biological evolution. Those are two entirely different groups of study. Very different. You can't overemphasize how important that distinction is. So you've got time, one set of experts, one set of techniques over here, and they couldn't care less about evolution. I kid you not. That's not what they do. But then you deal with process, which is the biology part, the evolutionary part. Okay? So very different, and different science and science involved. So you've got evolution, forms evolve, change through time, and then they go from simple to complex. That's macroevolution usually, big time. And what is the key word in both of these sentences? Scientific. And what have we said about the nature of the scientific explanation? We assume all explanations scientific must be materialistic or naturalistic explain. Non-material explanations are not necessarily wrong. They're just not science. It's a very important distinction, it seems to me at least. Okay, conclusions. The Earth is about 4.5 billion. Very simple life forms, about 3.5. Changes over geologic time point to a gradual increase in the complexity of organisms. There's been a series of fossils of our kind called hominins. See, I made a mistake. I had an M there. It's supposed to be an N. Ah! That's what happened when you do these at midnight. Dating back about 4 to 5 million years. And about from 40,000 years ago, we're the only ones left. The Neanderthals died out about 40,000 years ago, leaving just us. Okay? And the time scale is based on isotopic dating methods, not evolution. That's the take-home message if you want to take away one. So I don't know if anybody has questions. The issue of origin of life is a whole different issue. The type of biological, Darwinism, Darwinian evolution is one kind. It's not the only kind of evolution. There's other things that maybe some of you are interested in, I don't know. Or you may have others. Thank you very much.
All right, now is the opportunity to ask questions of Dr. Taylor if you'd like to. I will bring the microphone to you if you raise your hand. And you can ask anything you want. He is a brave man who can handle just about anything.
Just almost all.
Almost all.
I'm not a... Do you need some water? Yes, please. Thank you. I'm not a theologian.
Good.
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 That's good.
But I'd like to begin the questions by asking Dr. Taylor, with all of the dating that has been done regarding the age of the Earth or the time that homonyms have been on the planet, what is there a margin of error, plus or minus, on any of these numbers?
Oh my, yes. Okay. Oh, very important question. Thank you.
How wide a range is that plus or minus margin of error?
Well, potassium argon, for example, it's if you can get right now today, it's about plus or minus 5 to 10%. Okay. So if something is 100, thank you. If something is 100 million years old, 10% is 10 million. Yeah. Okay. Kind of every decade they get the error, what they call error. It's not an error; it's a confidence interval. Those are different. Gets lower and lower because they have new techniques of doing some things that reduce that.
All right. Thank you.
Oh, may I mention on radiocarbon dating?
You also have a microphone,
Oh.
Steve?
I'm just gonna run the microphone around
Very
where
good.
you tell me to.
Okay, go ahead.
In radiocarbon dating, now, today, if you date something at 10,000, your error term, I shouldn't use that term, your confidence interval, is, can be, if the machine is running right that day, the machine has phases. You can get down at 10,000, you can get down to about plus or minus 100 years.
Okay, all right. Do we have a question here? Yes.
I have read that there are traces of Neanderthal in current humans.
Yes, I'm told by my colleagues, and I just did a DNA myself. I have about 8% Neanderthal genes, roughly. And most European, if your ancestry is in Europe, you will have a, 4, 5, 6, 7, 8% normally. Africa, very little Neanderthal, because they didn't. Well, there are some. Have they found Neanderthal in Africa? No, North Africa. Yeah.
Occasionally, I will, in a derogatory sort of way, call someone a Neanderthal. Is that okay to do, or is it?
Well,
It's a real put down, isn't it?
No, actually, Neanderthals and us, they think because of the way in which the larynx is configured, they had some difficulty making certain phoneme sounds, certain sounds that used in language. And they may have had some limitations there. But the brain size is, with few exceptions, comparable to ours. They were just a rugged, very ruggedly built because they lived during the last ice age.
Yes. Sergio Santiago. Hold it.
See if I can trip here.
On the isotope dating, you need to put a starting point. And how do you determine the starting point of the decay? When do you start the timing? Of
It
the
depends
decay?
on the technique. For potassium argon, it begins when the lava or tuff cools down below the time where you can accumulate the argon. So you eliminate all the argon in the past, and your argon that you get is after the cooling. So it's a cooling event. In radiocarbon, for example, it's when something dies. That's the zero.
Argon is a gas? Is that just
Yes,
captured
ma'am.
in the potassium?
When potassium-40 decays, one of the products is argon-40, and that's the gas. All right. From a solid to a gas. Interesting, isn't it? No, well, there's a lot of cases like that.
I have two questions, if I may.
Sure.
Just a moment ago, you referred to the equipment. Can you clarify what types of equipment are used to assess the quantity of these isotopes? I don't know if
Right.
it's mass spec or another.
Oh, yeah.
And I,
Yes, that's exactly right. Most of the work done is on what are called mass spectrometers. All right? How shall I explain that? These are very expensive machines. And they basically separate the isotopes on the basis of their atomic weight. For example, C12 and C14 has slightly different atomic mass. And in a very well organized mass spectrometer, you can distinguish them, so you measure the ratios. And the closest one to here is in Irvine, California, at the University of California, Irvine. That has a AMS, it's called accelerator mass spectrometry. Okay, now a mass spectrometer that does potassium argon, I suspect they've got one at, I don't think they do it here, but they've got several, they have many mass specs, and at least one or two of them could do argon, potassium argon.
thank you. I have one more question.
Yes, sir.
You presented a slide with a number of question marks related to interrelatedness. Can
That's
you
right.
comment about any investigations undergoing now that may be looking at that? And if so, how would, if it could be done at all, the interrelatedness be assessed?
If you don't have DNA in your sample, I wouldn't call it guessing, but you're basing it on, you're basing your inferences largely on physiology of the bone, okay, or the skeleton. You assume that anything that looks like this and this have to be related in some way. But those arguments, those are really inferential. very highly inferential. There is no way that scientifically, that I know of, let's see if I need to modify that sentence. Could there be another way of doing that other than, well, there are well-known kinds of, in historic times, of how certain biological systems will move from type A to type B. You make inferences that are informed inferences. You just don't guess. So they have criteria, and you have to evaluate the criteria that they use.
I don't know much about this field, but I have a couple questions. One, like when Mount St. Helens erupted, they didn't expect life to come back. It came back much quicker than they ever thought it would, and I've heard of it in other places also.
Right.
And so my question also relates to the dating.
Uh-huh.
It seems to me there's a basic assumption that everything happens at this steady rate. And my question is, how do they prove that this happens at a steady rate, and that at some point in time maybe things speeded up,
Right.
or maybe it speeded up sometime earlier, and so you could be off billions of years
Right.
if that's the case. So how do
Right.
they prove that that
Right.
doesn't happen?
That's a good question. First of all, remember the word proof, never used in a scientific statement. We don't prove anything. We have high degrees of probability. We have a lot of evidence. Is it always 100%? No. But like water is always composed of hydrogen and oxygen, H2O. Is there another way to make water? Well, I suppose so, but they never found it. The answer to your question is a good one. Remember, each technique has the details down in the footnotes, okay? And some rocks are porous for argon, all right? They don't hold the argon very well, all right? So you may have a situation, there are a number of kinds of rocks that come out of volcanoes which are not very good for potassium argon work, okay? The first potassium argon dates began about 1950, so we've had more than 50, 60, 70, almost 75 years. And the people who do that professionally, there's been, 3 generations, graduate students and postdocs and whatnot, looking at this problem. And they pretty much figured out which kind of minerals will work and which won't. And today, they focus on the ones they know works by experiments. By work, I mean, it's a closed system. When it goes below a certain temperature, it's a closed system. And they've done a lot of experiments to demonstrate that. And that's what's good about science. I mean, one generation of scientists say, hey, this does this. And then the next generation says, I did an experiment, it didn't work that way. You got to go back in the laboratory, figure it out. Okay. So that's the case here. Potassium argon dating has been worked on, as I say, for 3 generations of graduate students and postdocs. So, and I often say to people, for example, I said, well, I can date something to 60,000, for example. Somebody asked me, well, what is if you could prove that nothing is older than 6,000? I'd love to. I'd love to. I'd be famous and rich. Unfortunately, I can't get the data. Data doesn't exist for that. So, just like my geology friends, worldwide flood. They would love to find a recent worldwide flood. They'd be rich and famous. Unfortunately, it's not in the geologic column. Sorry about that. But we'd like to. We all want to be famous, don't we? No, I guess not. We're humble. We're humble people. So, anyway, that's it. Did I answer your question? No. Ask it again, please. Sir? Oh, get the mic. Get in the mic.
Yeah, but he needs a microphone. I thought Steve was
No, he wants the mic. This gentleman. Yeah.
How do you prove, or how do they prove that it hasn't changed over a time period? You've looked at it, they've looked at it for 75 years. The Earth has been around billions of years.
That's right.
How do they know 5 billion years ago, maybe there was an ice age, an extreme ice age, and it just really changed how things happened then?
Okay.
Or maybe there was a real heat wave or something and
Sure.
it changed. We don't have that basis, we don't have that knowledge. So how do they prove, you know, I'm sure they've thought of that.
Oh,
how
my,
do
yes.
how do they prove that that hasn't happened? Or even if it did happen, things just progress at the same rate?
Right. Again, we don't prove anything. We just have a lot of data. But that's words. My impression is for the people who do this professionally, geologists and others, geochemists, I think what they rely on is consistency of the data set. That is, things work together. That is, if there was these kind of problems, it would show up someplace. It would show up someplace. Now, the nice one is something like changing the decay rate, right? How do you know that the decay rate of potassium has always been the same? All right? Well, the physicist, if you tell a physicist, a nuclear physicist, that the decay rates change over time, they will have a conniption fit. Because it can't. It won't work. You'd have to change so many physical constants that at that point, I mean, the whole thing is, you know, what's the point? So I would say the consistency of the data is what usually they'll look for. That is, if everything kind of looks like it works together, and now if they've got some anomalies, in my profession, in what I do, I would prefer to have a lot of anomalies. I would prefer to get a date on something that's impossible. It can't be. That's more interesting, to find out why. Why am I getting the wrong date on this sample? Particularly if this is the 15th time you've dated the same thing, you get the same answer again and again and again, and then this time you get a different number. Why? That's more important. I give you all kinds of stories about how this happened.
Okay, we have a question here and then here.
Can you give some understanding of the ice core work from Greenland, Colorado, and then tree cores?
Okay, right. Yeah, the ice core data from Greenland and Antarctica is very interesting. I don't do this myself, but I know people that do. And what you got is, in Greenland particularly, where this got started really well, you have got ice cores, they're about like that go down, I think one of them went down, I can't believe this, but I think almost a mile, all right? Now, what's interesting about ice cores is that you can see the lamina. That is, you can see annual ice. And you can demonstrate that these are annual by part of that one has spring pollen in it, and the other part of the same year has fall pollen in it. All right? So they're known to be annual. All right? And the one that goes down the farthest right now, that you can actually see the lamina, I think is on the order of 500, 600,000 years. 100,000. 600,000. And there are those that are down to 800,000, I think, as they can count. But the problem is you get down farther and farther and farther, they get squeezed together. They're harder to make out. Okay. Anything else?
Well, tree cores.
Oh,
and the
okay, those are
explanation
different.
Of how they try and correlate. The core, the
Okay, now,
lamina.
yeah, tree ring studies, dendrochronology, are used for relatively recent material. Trees, we know trees are, most trees are annual, well, certain kinds of